this, it's at top too.
Yeah.
Oh god, so you pull an x out, you get x minus 4. And then on the bottom, what would I even do? So this is x minus 4 times x plus 1. Left-handed, you can't see. And then, so you can cancel that, and then you're just left with x over x plus 1. And then if you plug in 4, you get 4 over 4 plus 1, gives you 4 over 5. And then x cannot be 4 or negative 1.
Agree with Steven?
That's it.
And please group. Okay, good job.
Thanks.
Then read it.
Okay. Oh wait, can't move that. So you have to fill the top, and you'll get 25 minus 10 each. Then you have 1 minus 25 all over h. Your 25s cancel, your h's cancel, so you're left with negative 10 plus h, plug in 0, and get negative 10.
Screw up.
There you go. And then, of course, h cannot be 0.
Agree with Green?
Yeah.
Neat. Good job. How about you group? Same answer, right? From both question A and B. Okay, very good.
Wow, that's very good to see you guys for, doing both of the questions, and you got a correct answer from both question A and B, okay? Alright, so I will just talk about these two questions very quickly before we move on to the next page, okay? So here, given factor, both top and the bottom, okay, and then here we have this common factor x minus 4. Well, here, how can we cancel out x minus 4 directly?
X minus 4 can be 4.
Yes. Why x minus 4 cannot be 4? Because when x approaches 4, it means what? X cannot be 4. Remember, when we talk about approaches from both sides, that means x cannot be 4. If x cannot be 4, x minus 4 cannot be 0. So of course, we could cancel out the x minus 4 from both top and bottom. So that's how we get x times 1 is x, 1 times x plus 1 is x plus 1. Then, for this rational function, what is the domain for the rational function? X cannot be negative 1, right? So this x equals a is 4. 4 will not make the denominator equal 0. So 4 is in the domain for the rational function x over x plus 4, right? So we plug in x by 4, give us 4 over 5. Right, everyone? Yeah, here, just want to emphasize for one thing. Are we able to cancel the x minus 4? Yes, because x minus 4 cannot be 0, and because we have x approaches 4, gives us, right, that. Question B. Yeah, the tricky part is, the first time, we substitute h by 0 from both top and the bottom. Give us negative 5 plus 0, parenthesis square, 25 minus 25, 0. So on the bottom, 0 is also 0. So 0 over 0. So it's undetermined. Can we see that?
No.
No. We have to simplify it, right? And because this is a square, for you, will compute as a complete square. That gives us what? Careful here. Negative 5 square is what? 25. And then plus 2 times negative 5 times h give us what? Negative 10h. And then plus what? H squared. So this is how we get these three terms in this parenthesis, okay? And then minus 25, we copy that term, the negative 25, and then cancel out. Well, here, we have a negative 10h plus h squared over h, okay? So bringing cancel out all of these h, that's good. Well, we can rewrite it like this. Hopefully this will make you guys, see better? Okay, so from negative 10h plus h squared over h, because every term from the top has a factor h, so we factor the h out, coming, right? We factor the h out, give us negative 10 plus h, right? Well, here, we want to find the limit of h approaches 0. Common factor h, can we cancel out h now? Yes or no? Yes, because h approaches 0, give us h cannot be 0. Oh, gone. Okay, so now we have a negative 10 plus h over 1, okay, which is negative 10 plus h, okay, and when h approaches 0, it gives us negative 10. Answer is negative 10. Everybody, are you clear for both of the questions? Okay, so very good. Okay, so these are the two practice questions to compute the limits. Okay, see, a lot of times we have what? 0 over 0, okay, case, but it doesn't mean that we don't have a limit. Okay, so we have to simplify the function and then keep on keep on doing the problem. Okay. All right, so these are the practice questions. Now let's look at the third page. Okay, third page. We have some theorems, okay, important theorems involving the limits, okay. For this theorem, I'm going to ask some of you guys read the theorem for us, okay. So let me see whose turn. You read it, Sunny?
It's not in here.
Oh, I modified the notes this afternoon, okay. So you will see the updated one in the modules.
Okay, it says theorem limit x over a, f of x equals L, if and only if limit x over, is that
That's A minus.
Yeah,
a minus?
yeah,
Is that the right or left hand limit?
yeah, this is the left hand limit, right?
Left hand limit, f of x equals L, limit x over a, right hand limit, f of x.
Okay, very good. Okay, good. Do you feel this theorem looks familiar to us? We actually did it last time. It's a repeat. This is not a new for us, okay? Why?
It
Because,
won't exist otherwise.
well, yeah. Remember last time there's no L, okay? We talked about, if the limit of f of x when x approaches a exists. And then even only if the left hand limit equals the right hand limit, right? But there's no L. This time the new part is equals L. We have a specific value for the limits, okay? So what does this theorem tell us? Okay, the theorem even only means equivalent to, means from this direction to this direction, it will be true, okay? So that means if the limit of f of x equals L as x approaches a, it will imply both of the limit must exist, and then they must all both equal what? Value L. Okay, remember the graph we talked about, okay? So when x approaches a from both sides or whatever the graph looks like, okay? So, yeah, so, so the limit of f of x equals L, okay, from both sides, this is the meaning, okay? It will implies the left-hand side limit exists and equals L, right side limit also exists and equals L. Reversely, same thing, guys. Okay, same thing. If both of the left hand limit and right hand limit exist, and then they both equal the value L, then it will implies the limit from both sides exists and equals L. Okay, so this is a conclusion from this theorem. Now, question for you. How about if we have the two hand side limits, they exist, both of them they exist, but they do not equal each other. Can we say this limit exists? Yes or no? No, okay? But say for example, if I draw a picture for us, say this is a value, okay? This is, left hand limit, the other one is right hand limit, okay? Even if both of them, they are existing, but they're not equal the same value L, we cannot say that this limit when x approaches a from both sides exists. No, okay? Only if when both of the two hand side limits exist and equals same value L, then this whole thing, this limit exists and equals L, okay? Reverse it, same thing, okay. Now we have these two examples to let us, show or prove limit of the x value function x when x approaches 0 equals 0. How can we prove x value function when x approaches 0 equals 0?
Well,
Dakota?
if we can prove the limit of x equals 0 and the limit of negative x is equal to 0.
Yeah, so in order to prove this limit exists, how about we prove when x approaches 0 from the left, right? What is the x value equals, okay? We're also going to try when x approaches 0 from positive, positive 0 and, 0 positive. If these two hand limit equals each other, then the whole limit will exist, right? And if we want to make sure that both of these two hand limit equal 0, then the whole entire limit equals 0, right?
Let's plug in point 1.
Plug in point 1, okay. Well, the thing is,
There is no reason not to plug in 2.
what is a function in this problem? X value function, right? So for x value function, we can consider it as a piecewise defined function. What are the piecewise? When x is positive, x value of x is what? Equals x itself. We learned this before, right?
Right.
When x equals 0, what's the x value of 0? 0. When x is less than 0, what is x value of x? Negative x. Right? So if we take a picture, this graph should have 3 pieces. What are the 3 pieces? When x is positive, y equals x. You should still remember what is the brief shape of our x value function. Looks like a V, right? Yeah. When x equals 0, y equals 0. When x is less than 0, y equals negative x. It looks like this. So this is the graph for x value, function. Now let's talk about this left-hand limit and right-hand limit. So when x approaches 0 from the left, like this, right? How about y value approaches 2? Can you see? Can you tell? X approaches 0, y also will approaches to what? 0, yes, it will. Because when x approaches 0, x value of 0 is what? 0, right? And then when x approaches 0 from the right, what's x value of x? Approaches 0 as well, right? So the limit is 0.
I knew that, but when they said prove it, I thought they wanted you to show the number. I wanted to say the two absolute values of the positive and the negative number that are equal, and show the absolute value.
Yeah, you can. Yes, you can. We can. Say this part is when x approaches 0 from the left, means when x is less than 0, we know in this case, because x is negative, x value of x becomes negative x, right? So x approaches 0, negative will give us 0, right? So for this piece, we can get rid of the x value, give us what? Well, x is positive, x value of x is positive, right? So, yeah. Either from the graph or from, this like more mathematically way. That's, yeah, good, okay. So, and now because both of the hand limit equals 0, we say, this entire limit equals 0, you guys? And then you can say thus, or so, limit x value of x when x approaches 0 equals 0. Because of these two, so the entire, limit equals 0 when x approaches 0. You guys, this example? Now next example, let us prove or show that the limit of x value of x over x when x approaches 0 does not exist. Does not exist, just now we talked about. In order to prove the entire limit doesn't exist, we can try what? The two limits, right? Two hand limits, left-hand limit and right-hand limit, and see whether they exist or equal some specific value or not, right? So let's try the left-hand limit. So Just like Simon just said, we use, the mathematical way to do it. We know when x approaches 0 from the left, x must be less than 0. If x is less than 0, absolute value of x must be, well, how do we get rid of the absolute value sign? Negative x, right? Limit x approaches 0 negative. This becomes negative x because x is less than 0, right? And then divide by x. When x approaches 0, x cannot be 0, cancel out. So what do we have actually for the left hand side of it? It equals negative 1. Okay? And then right hand limit, okay, because x are positive, to get rid of x value, give us positive, not positive x, it gives us x back, and divide by x. X cannot be 0, right? So, what do we have? 1. So indeed, they're both of them, they exist, but do they equal the same value? No, okay? So one has a, value negative 1, the other one has a different value 1, right? So because they don't equal the same value L, we say this entire limit does not exist. Do you see that? Okay. So we say limit when x approaches 0 from both sides, value of x over x does not exist. Everybody clear about this theorem? It makes sense, right? In order to get the entire limit, exist, we must have both of the, left-hand side and right-hand side limit exist, and they have to equal the same value, right? Reversely, same thing, okay? All right, we have 2 more theorems in this section, okay? So, this theorem, I'm going to ask a volunteer to read it, okay? Who want to read? Anyone? Nobody? Okay, let me see whose turn. Oh! And a volunteer attendance?
I'll do it.
Okay, Simon.
Yeah, it says, if f of x is less than or equal to g of x when x is near a, except possibly at a, and the limits of f and g both exist as x approaches a, then the limit of x to a, of f of x is less than or equal to the limit of x to a, g of x.
Okay, very good, okay? So this here is telling us if function f of x is less than or equals g of x. What does this less than or equals to? Say for x, y plane, okay?
Maybe lower on the graph.
Yeah, you're right, okay? So we say this is function f, okay? And then there's another function, say g, okay? Okay, so when x is near a means x could be approaches a from the left or could be from, approaches a from the right. So this lower one is f of x, the upper one is g of x. You're right. Greater than, or means on the top. Less means on the bottom. Okay, you're lower. Okay, lower. Okay, if these two functions satisfy f is less than or equals g, okay, blah 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 this, then we say the limit of f of x is less than or equals to limit of function g of x when x approaches a. Okay, well here I'm not going to prove it, okay, so you can read the textbook and see whether there is a proof in the book or not, but this is like geometrically we can tell, right? This function f is less than or equals to g, then when x approaches a from both sides, okay, they may have the same limit, or here I don't want to draw any intersection over there, but I mean g is on top of f, okay, so the limit of f is less than or equals to the limit of g, okay. Alright, the next theorem actually is an extension, okay, extension from this theorem. This theorem is called a squeeze theorem, okay. There are 3 functions involved. F of x less than or equals g of x less than or equals h of x, okay, when x is near a, okay, except the possible at a, okay. So I'm going to draw a picture. Okay, so three functions. Here, functions in the middle, a function is on top. Okay, so for example, this is f, this is g, and this is h. Okay, well, x is near a, okay, except if possible at a. Okay, all right. Well, here it says the limit of the lowest function equals the limit of the highest function. Okay, when x approaches a equals to what? L. Geometrically, can you tell? Does this graph satisfy the limit of f and limit of h when x approaches a equal the same L? If there's a touch, okay, the intersection of all of the three, what do you feel? What do you think? Yes or no? Yes. Okay. So all of the three graphs, they touch each other at here when x equals a. Okay. So, yeah, well, we don't care about this when x equals a, actually. We don't care, okay? But we know that when x approaches a from both sides, the limit of f equals the limit of h. And f is the lowest one, h is the highest one. Then the squeeze theorem is telling us the limit of the middle function g when x approaches a must also equals what? L. It's like a sandwich. Like two bread, inside there is a meat, okay, like chicken, whatever, ham or something. Yeah. Okay, if the limit of these two bread equal the same value L, then it squeeze the middle function, it has the same limit, which is also equal to what? L. That makes sense, right? See? The lower one, the upper one, the top one equals L. Then the middle one, it has no choice. Function g has no choice. It has to, the limit of g must equals L. Okay. Okay, so the squeeze theorem, this is something, I believe this is new for most of us, okay? So I would say we can use squeeze theorem to do some practice questions, okay? So now this example, I hope after we talk about squeeze theorem, this question should be straightforward for us, okay? Yeah. We have three functions, f of x equals 2x, g of x is in the middle, and this function is on the top. Okay, this is f of x, this is h of x. They want us to evaluate this limit of g when x approaches to 1. We have no idea about what g is. Do we have any information about g is defined by what? No, nothing. But we know g is squeezed by these two functions, f and h. In order to find this limit of g, what should we do? By the squeeze theorem. By the limit of f and h respectively, and then see whether they exist and equal the same value or not. If they do, then we can get the limit of g. Do you see that? Okay, so limit of f of x when x approaches 1, we know f of x equals 2x, right? Okay, can you please give me the answer for this limit? 2. Yeah. Oh, these three functions satisfy this. Also, we know the limit of these two sides functions, they all exist and equal the same value, true. How about the limit of the middle function? Should be true as well, okay? Yeah. So, limit of g of x when x approaches 1 must equals what? 2. By using the squeeze theorem, right?
Yes, I was just going to, could you remind me how we know that the h of x is limited by 2. I don't realize how we got that.
So the limit of h of x equals 2.
Yes.
Because this is a polynomial function, right?
Right.
For a polynomial function, there's no restriction for x, so we just use a direct substitute property, just substitute x by 1. So 1/4 power is 1, 1 square is 1, 1 minus 1, 0, 0 plus 2 is 2. Yeah, you're welcome.